So if we want to look at a few more details in this mechanism, we can look at the energy diagram for it, or the reaction coordinate diagram, where we're looking at the relative stability of all of the points along the way of the reaction. So starting with our reactants, this simple alkene have a certain energy associated with them, the bond energy, the stability of the charged molecules and such, right? We go up to the first transition state before we go down to the first intermediate, right? So this is our intermediate in this mechanism, and then down to our more stable products, right? And so if we're looking at energy diagrams, that's a descriptive way of talking about the stability of the reactions, but also the speed, the relative speed, sort of a qualitative look at the kinetics of the reaction as well. So if we're here, this highest point in energy, this transition state here, that would be somewhere between our starting materials and our first intermediate. This is the hardest thing to do. It's the highest part of energy. It's also going to be the slowest, right? So the highest point is kind of like a roller coaster going up a hill. Like it takes the most energy to get to this point, and then everything else is sort of downhill from there and relatively fast. So this is the slow step. The rate limiting step of the reaction is getting to that first point. And the energy of this transition state has a lot to do with how stable this intermediate is too. So in our 1-2 mechanism, and if you're not sure what that one is, check from the previous video, the intermediate of the 1-2 mechanism was the less stable primary carbocation, right? So this primary carbocation can form, if we're doing the 1,4 addition, we start with the same products, but we have a less stable intermediate. So this is going to be slower, right? This is going to be slower to form, harder to make in general, but the product of that reaction, so this is our 1,4 intermediate. The product of that reaction actually has the more stable alkene in it. Right, so the more substituted alkene in between these two carbons is a little bit more stable than the 1,2 product. So if we can actually get to that point, if we can get to that higher energy point, then we make a slightly more stable product. So when we're looking at these energy diagrams, we're kind of showing the mechanism, right? We're showing any intermediate along the way and its relative energy. We're showing how fast the reactions go, right? So in red, our 1,2 addition is faster. So we call that one the kinetic product. Right? So relatively easier to make, but if we can go in this more difficult route, we can end up making a more stable product. In this case, this is a slower route, but in this case, and not in every case, it makes a more stable product, which we can call the thermodynamic product. Right? So our difference in energy from start to finish informs us on thermodynamics. So if we're going from a high point to a low point, these are thermodynamically favorable, right? So we end up lower in energy and making more stable products from less stable reactants. And that's generally favorable, but the mechanism, the route it takes to get there matters too. With a more stable intermediate, it has a lower barrier for reaction, so this reaction can happen sort of faster and easier. And it's a good test case that most books cover doing these reactions of conjugated dienes. They can be more complicated. A two paths, one could be kinetically favored, but also thermodynamically favored. There's a lot of variety here, but this is a good way to kind of introduce the topics. So how do we get one product and not the other is the good question then is, well, how do we overcome these barriers in the first place, right? So if we're in the lab, a lot of reactions might just happen at room temperature. We mix the two things in. The reactivity is such that it will just go, right? But there's still heat involved there. Room temperature is still a temperature. So to get to these higher barriers, usually you just add more heat, right? So a hotter reaction done at elevated temperatures is more likely to be able to break this barrier, and then more likely then to give you the thermodynamic product, right? If we don't want this product, doing it at lower temperatures is going to favor the kinetic product, because at lower temperatures it's harder to get past that first reaction barrier.